Hi there, let's work in tutorial 8. So I love this tutorial because we can use it as a playground to play with different runs models, turbulence models. So this is the classical incompressible flow over an NACA 0012 airfoil. I hope you have seen that. So here I'm giving you the data again. You can download the Fluent case. Okay, we're going to work through with this case, and then you have here the experimental data we are going to compare. So that experimental data is taken from here. Also you have this link. So just to show you, we are basically reproducing exactly the same case. Okay, we're using NACA mesh. Also, I don't recall the Reynolds number that we're using, probably 6 million or 3 million. There are different Reynolds numbers, but you can get it from the case, the velocity and the density, the properties that we're using. So here you have all the data. So we're reproducing exactly the same data. So it might seem that this case is an easy one. So here you have lift and drag behavior, but after 30 years that CFD have been around, it's not very easy to predict this one, the maximum lift and the stall. So we're going to work with small angles too, but you can feel free to reproduce the whole stuff. And here is where you're going to get into problems. Predicting the stall is tricky in CFD. It requires some experience. So let's work in this case. Okay, so the geometry, by the way, also the two reference that I'm giving you here, you can download from here the two reference, but also they are free. You can find it in the internet, the NASA website, you can get it. But these are the reference, or the data also you can get it from here. There are different, many cases that you can model here. So it seems to be all, probably you will say, okay, 87, but it's very valid, okay? So interesting reference, you just have to take some time and go through this data. Okay, so let's run the case in Fluent. Again, it's a 2D case. So when you open Fluent, launch Fluent, remember just select 2D, double precision, and choose the number of processors. So I'm running with 2. Okay, these are an expensive case. So as you look at the mesh, this is a very nice mesh. And as we go into the airfoil, we need to zoom in, see that this is definitely, it is a well-resolving mesh. Okay. So let's work in this case and let's go through the setup. Okay, the one I'm giving to you is already predefined. So as you go to general, see that we're working with pressure based, always steady. Okay, and then you go into models. Here's where you enable all the models. So here's where you can play around. So I'm going to run here. You have a K omega, but I will choose this parallel matters. We went through the theory about this one. This is a model that was specifically formulated for this kind of problem, aerospace applications, aerodynamics. But I will go with this method, but you have all this method, different setups, arrangement. Okay, so let's go as parallel matters. Then we keep reading here, boom, no more models. Then we go to materials, we choose our working materials. So let's use air, standard conditions. Okay, we don't change anything. In cell conditions, materials, here you define your materials. You have more than one. Okay, you choose your material or source there. And then we go boundary conditions. Okay, so here we have, in this case, we have an inlet, all this blue surface here, and an outlet. So as you go into inlet, we have this input value. So you take this velocity, you have your fluid properties, and the airfoil core is 1 meter. So you can compute your Reynolds. I think it's 3 meters or 6. It doesn't matter. It's up to you. But we're comparing with some experimental data. So in this case, we are going to run for an angle of attack of 2 degrees. So this is something important. This is an error that I see people does a lot. Okay, so remember that lift and drag forces are perpendicular and parallel to the flow. So if you choose to have this geometry, this kind of setup where your airfoil is fixed, it's not rotating, you will need to give the flow direction. Okay, you alternatively, what you can do is rotate the flow, and this will be always 1, 0. But is your incoming flow, you're giving an angle here, you will need also, when you compute the lift and drag, we're going to do it, you will need to give this rotation matrix. Okay, so just to make it clear here, let me draw screen. Okay, so basically, if your flow is coming in this direction, okay, the lift and drag forces are, lift is perpendicular and drag is parallel to this one. So you will need to rotate how the flow, the forces are computed. Very important. Do not forget that, because I see people just consistently make this error. Okay, so you set up these quantities, okay, velocity, magnitude, the flow direction, and then we give the specification of the boundary condition for the turbulence model. So in this case, we're using spiral matters that only takes the modified turbulent viscosity. So we saw the theory, something between 1 and you can put 1 and 10. So let's use here 5. Okay, it's up to you. Then the same for the outlet. You go into the outlet, it's a pressure outlet, so you fix your pressure here is relative to your reference pressure. That, remember, reference pressure is set up here in cells conditions, operating conditions. So we're working atmospheric conditions, okay, don't forget that. So set up your values here, okay, just backflow values. We put 5, let's put 5 also here, and these are our boundary conditions. So the rest is wall, okay, and then internal is set automatically, internal cells. So we go through here, mesh interfaces, nothing, dynamic mesh, nothing, reference values. So let me enter here. So now we're going to compute coefficients, CL, CD, CM. So those coefficients are normalized using this reference value. So you need to give it here, okay? So, you know, your airfoil, everything. So if you have this value, you press inlet and you will use the inlet values for velocity and density. So these values are okay. This will be used to normalize CL and CD. Okay, I hope you recall how to compute those. Then we go reference frames, nothing to do here, nothing to do here. And then we move into solution. So here you have the method that you can use. Okay, so again, as I was telling you, if you are steady simulations, probably this is the best choice, but feel free to use any other method. Okay, and let's do the experiment here. Let me choose here second order upwind. Okay, we talk about this, and these values are okay. And see, here's where you create the report definition. So let me recreate another one. So I will create another 4 forces here. So I want drag. So say that I will call it, you give it a name, CD2. So what you want to compute, the force or the drag. So if you compute the force, no, you need to define reference value. Drag coefficient, you need to define those. And where do you want to compute it? I want to compute it here at this wall. And then you just say, okay, I want to plot it. So I will have a new tab there and print it to screen. Additionally, if you want to save it to a file, you put it there and you save it. Okay, so choose all these 3 options, okay, because also we want the file, okay, just to play around. And you have everything predefined, by the way, so no need. You have everything here, but remember, before moving, you need to set the force vector, because so far you have your flow coming at 2 degrees, but this flow vector does not correspond to that. So here you will need to take your your rotation matrix, okay? So you know the 2 degrees and you put it here, okay? So remember that you have 2 vectors. So here will be cosine, sine. Okay, let me recall for drag. So for drag will be cosine of 2, sine of 2, and for lift will be minus sine of 2, cosine of 2, or cosine of your angle of attack. This is a rotation matrix, okay? So how you recall that. So this is how you set up. As usual, set up the Y plus. I always like to set up this one, and any additional report definition is up to you. So now we go into monitors. So here we go into residuals. So let's use the standard residuals. So here I put this one so we can go like this, okay? You have everything here, and now let's move in this new condition. So here we have the converse conditions, okay? So remember that your solver will iterate, and if it reaches this condition, it will stop. Okay, so sometimes it's like a problem that will reach it really fast, but your coefficients will still oscillate. And so it can be a good idea to add also a converse condition to your to these quantities that you are monitoring here. So that you can do it here, converse condition. So if you right click, create, let's create a new one, okay, add, give it a name and leave the default one. And what do I want to monitor? So let's say that I want to monitor lift coefficient. You give it a stock criterion. So for me, usually this is a percentage, okay? So if you put it like this, it's 0.1 percentage, okay? So I usually like to use this value, and then do not compute in the first 10 iterations. And to reach this convergence, just use the last 10 iterations, okay? So you put 100, you will need to compute those statistics in 100 iterations and see that if it's not oscillating more than this quantity. So 100 is a large value. So I like to use 10/10. So in my personal experience, I have found that these values are okay. Sometimes they can be really low, so you will never reach this. But again, you can play with this one. Sometimes you switch off everything and iterate up to a point that you think that you can stop it and do your statistics. So I will stop it, but again, some of your stuff here, well, you can print this one in the terminal, and then you can choose to compute this every single iteration, okay? If you put more of this, or you can add more, you can say that all conditions must be met or just one, so you see that you can add it and delete it there. Okay, so we added that, then we go to initialization, so let's compute here. Okay, see that we have our values initialized. Okay, but this is a uniform field, remember. So uniform field, in this case, we can take advantage of that full multi-grid initialization. So remember that you have here in the text user interface. So you go solve, init, and now fng, yes, and we're going to use this initialization, very powerful. I love this method, but as I told in the previous one, it's not available for every case or every physics, okay? So see that we have a very good initialization also for pressure. Okay, so now that we did that, what else we can do? Initialize, and we're ready to run. Okay, so choose number of iterations. So in this case, it might take a lot of iterations to converge, who knows? So I put 10,000, but remember, it will stop when both of these conditions are reached. Okay, so you need to reach residuals on this one. Okay, we're going to see that. So press calculate, and okay, so here it's giving me this warning because I already have another solution, and it's telling me that these coefficients, that remember that are 7 down in a file, what you want to do this, you want to create new files or you want to overwrite. So I don't want to create new files, okay? So it will ask you to confirm, okay, do you want to overwrite? Yeah, so overwrite that data, but have in mind that if you want to keep it, just move it, okay? And this is what we have. We have all our monitors, everything reported here. And let's wait a little bit. So just to point out, see here that in the first iteration it wasn't compute this condition, and then it's been compute, okay? And this is the second convergence criterion that we're using. So see that the solution already converged. Okay, this one is already converged, but I still need to converge the residuals. And see that now my residuals converge after 56. So this is very interesting to look at this plot, okay? So see that the first 20, as we say, do not compute, and then I start to compute the statistics, okay? So when you meet that criterion, stop, but check if you meet the other one. So see that your report definition has converged at 57, but your solution also converged in 47 that you see here, okay? And actually here you can see that they are not oscillating anymore, and then also you have this good behavior here. So we can take this solution for granted, okay? Then you can plot as usual quantities, okay? So here, yeah, you have your velocity. So see that, remember your initial conditions. So see that these ones are, the final solution is very close to the initial condition. So this is why we have this super fast convergence rate. Is you have a standard initialization, it will converge as well, but probably will take twice or 3 times that value. Then you have all your turbulence quantities, okay? As we have dealing with that. So let's take a look. So here modify Turbulent viscosity is where your turbulence model is, let's say, kicking in, okay, where we're expecting in the wake and close to the airfoil. Then you have your turbulent kinetic energy, okay, we have here turbulent viscosity, okay, this is the normal, they are related, so it's multiplied by that factor, as you recall the equations. So you can feel free to explore that. So your viscosity ratio, so remember that the turbulent viscosity is much larger, so this is than the molecular one, so this is telling you that ratio between turbulent viscosity and molecular one, okay, so you have all that information there, you can access many more data there. In this case, what we're interested in is just in comparing these two values with the experimental data. So as you go through the data you downloaded, you will see that you have this file. As you open it, this is experimental data that we have for the NASA website or those papers. And we're working in 2 degrees, okay? So let's see how far are we from this. So you see that it was very fast, very easy to set up. So actually we have 0.22, okay? So not bad, I have to say, in just less than 100 iterations, okay? And then the next one was 0.008381, not bad, okay? So see that, and then this is the playground, because now go and use use K omega st, K epsilon, Reynolds stresses, any of the other turbulence models, and you will see that there will be some differences. So each turbulence model will give you different results. Hopefully they will be all close to these ones, okay? But this is the idea of turbulence model. The turbulence model will add that quantity that will stabilize everything. And why do I use that word stabilize? Because now let's rerun and let's switch off the turbulence model. So imprint in your mind, in your brain, in your eyes, this behavior, okay? See that is very flat. So let's rerun, but now to rerun, let me initialize. You can switch it off, the model here, but I don't want to switch it off. I will show you another options. You go here into controls, equations. Here you can choose what equations you want to solve. So if you deselect this one, you are not solving modified turbulence viscosity. So at any point you can click here and then you solve it. So this is a way to switch off and switch on equations in your simulation. So you can have here many equations if you have more models, so you can select what you want to solve here. So deselect, initialize. So as you go here, see that you need to initialize it. Well, you need to initialize because it is enabled, but we're not solving this equation as we're going to see. So if we run now, this end, so item 1, override, yes. So look at residuals, see that we're not solving anymore that equation. Okay, and let's see our behavior. So we have everything, but now immediately we see that it's oscillating. Okay, so even if this is the goal, the scope of all these turbulence models, okay, is that additional quantity that we need to add it to make it physically realistic. I'm not saying that what we're having here is not physically realistic, but remember that if you input turbulence models that are doing theory DNS, you are solving the exact Reynolds Navier-Stokes equation. So you need very fine measures, and you need to work also on steady to capture all scales. Okay, so see that everything here is oscillating. Okay, so you're computing a solution. Okay, and it's okay, it's converting fine, but from the physical point of view, these values are very far away from what they should be. So as soon as we enable the turbulence model, everything will be stabilized. But see that the CL is not far, okay, but it's oscillating. This is just telling you that you have flow separation. CD is also oscillating, but we have that scale, but you see it here that it has very large oscillations, okay, and this one probably is far from this actual value. So these oscillations, you mean this value probably will be close, but if you take the average of this one, it will be a little bit far. Okay, so let's stop and see that the residuals they have another behavior. So usually when you see that they stall like this, doesn't mean that the solution is wrong. This is just telling you that you have an unsteady behavior. It's better to switch to an unsteady solver. Okay, and let's plot the solution here. Probably we're going to see. Okay, so let me zoom in. Okay, and see that you have here some flow separation. Okay, in the case with the turbulence model, it was very stable, but here you see that you have some separation. Okay, and we can go also pressure, and probably we can see here that you have the shedding. You have some vortices that are being shed here. Okay, boom, 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 and this is what is happening in this case. Okay, as you are resolving all the scale, you have this scale arm, as you are not capturing the right physics because you are missing also your unsteadiness. Now you are in a steady mode. Probably this is not very realistic, these quantities that you are averaging there. And if we go here now and we now enable that quantity and we keep running, let's see what happened with all these quantities. Okay, so see that I enable those. See that now we're resolving the turbulence equation, and see that you already see immediately behavior, much better behavior. Everything is stabilizing. See that now CL is stabilizing about that value, and see that CD, well, it's difficult to see here, but also here is stabilized. And this is the this is what turbulence models are doing. Okay, are modeling that additional quantity that we have seen in when we derive our solvable Rance equation, the mu T, or the molecular viscosity plus the turbulent viscosity, that effective viscosity that we're computing with the turbulence modeling. And clearly in this case you see that effect. So okay, I can stop it now. I can go back here and see that here we don't have any more of those vortices being shed there. You have everything, no more separation there. So clearly the influence of the turbulence models. So again, feel free to play with all these case turbulence models here. Okay, play around a different angle of attack. Okay, and try to reproduce these results. Okay, this is hard. Honestly, it doesn't matter if you are new or you are very experienced. Getting here is really hard, and probably you need to use some other models specifically to deal with this. But as you stay in this linear regime, let's say between -10 to 10, you should be able to reproduce very well lift. Okay, solving for lift is easy. For drag is a little bit tricky, but also you should be within these values. Okay, so try to reproduce this. Also, if you want, you can plot CP in the surface, so you have your CP's distribution there. So just to show you how to do that plot, again, you go in plots, XY plot, and you can put here new. You choose where you want to plot. I want to plot in the surface, and choose your quantity. So for instance, I want to see the Y plus value, turbulence, wall Y plus, and here you have your Y plus. So this is a wall resolved mesh. Okay, and remember that it's almost impossible to keep it constant. Okay, and then you can plot also pressure, and this is your pressure distribution. Also you have CP here that has been normalized using the previous coefficients. So see that we have it here, 1 the peak. Okay, the stagnation point, your distribution. So to have it with the aerodynamic plots, you need to invert the axis. Okay, so usually this is multiplied by -1 and you invert it. Okay, it doesn't matter. So this will be the suction and pressure side. Okay, pressure side and suction side. So intradose, extradose. Okay, so that was all for this case. I hope you will enjoy it. I'm sure that you will enjoy this case. Very nice case. So feel free to play with all options, and see you next tutorial. Bye.